triple Arduino pulse counter sequencer attenuator. Triple AND gate, dual, 4-channel software controlled attenuation, expandable up to 8 or 10. LM317 voltage output, IRF P460 low side drain, isolated differential across the exciter cavity, sequence amplitude of varying proportions, controllable by the gate and pulse counts, as well as for input frequency from the external signal generator. Can be slowed way down to see the effect. First test with the B plus only dual rail output, LM317, LM337, dual channel attenuation, although one side is not currently connected. This is obvious. The negative side still having some difficulty with pulling it down equally. Slew rate makes it unmanageable in my opinion. 2N7000 MOSFETs, 5K Rs. Pull down the adjust pin. Approximately 70 volts AC from the variac. You got 0 to 120 control with current limiting. Step down 6 to 1. 12 0 12 out. Input into the power supply module. Pulse counter, attenuator, and triple AND gate output fed to IR 2110 PB gate drivers, dual. Only one side is connected at the moment. Salvage heatsink with electronic cooling. Sequencing is directly bound to frequency. Attenuation can be non-linear, unlike the typical decade counter demultiplexer CD4017. Software can control the sequence to not be linear. Independent gate off time as a count of periods. Pulse count as T3A on time. Varying attenuation. This unit can take roughly max 70 volts peak to peak AC. Split down the middle, so plus 35, minus 35, 40 volts max per regulator. Capacitors are rated at 50 volts, can't go much more over that per side, so about 70 volts peak to peak is the max input of this board. I did remove the output filter caps. They were these little guys right here. Little 10 microfarad jobbies. 35 volt. 100 microfarad, sorry. That's even worse. Discharge tail on the LM317. As the attenuation is changed, the adjust pin is pulled down or released higher. Rise and fall, what is effectively becomes rise and fall, is a very slow transition period. Very slow. While it's easy to observe at low frequencies, it's unperceivable at much higher frequencies. An averaging effect occurs, and at 10 kilohertz it averages so much that it's nothing but a slight ripple. 20 kilohertz, pretty similar. Very slight ripple. 100 kilohertz. Almost no change. And the signal generator is about hitting its limit due to the logic. Almost no attenuation at 60 kilohertz due to the averaging. If we go back out, you can see the attenuation resume. Plenty of time for it to transition. Output was about 12 volts here on the positive side. So as you can see, very low current.